this video, we're going to be dealing with calculations involving equilibrium expressions. I have 3 questions here on the page. This would be a great time to hit pause, try them out on some paper in your notebook, and then come back. All right, welcome back. Hopefully you got some of these answered in your notebook, and now we can go over the questions and answers. First things first, we've been talking about KEQ, the equilibrium constant. Today in this video, I'm going to be using the expression Kc. It's the same thing, but this time the C represents concentration. Let's start by looking at our equation to verify is it balanced. 2 moles of iodine react with 2 moles of bromine in a reversible reaction to form a single mole of iodine monobromide. Okay, so we have monobromide, which tells us there's only a single element of Br. But when I look over here, there are 2. So we go 2, and then we check our iodine, and now we're balanced. Okay, so that's not meant to be a very big learning lesson here. Just some quick reminders for you. Then we read the question. It says at 250 degrees Celsius, an equilibrium mixture in a 2-liter flask, that's important, tells us that we're not going to be given concentration values, contained 0.24 moles of I2, 0.5 moles of Br2, and 0.4 moles of IBr. What is the value of Kc? So there's our question. So let's start by writing down our Kc expression. It's the exact same as KEQ expressions. So I write down Kc equals, throw my ratio sign down on the page, and then I look to my balanced equation. Remember that products are on the top, so IBr in square brackets, and we're going to raise that to the power of 2. It's stoichiometric coefficient. We're then going to put the product of our reactants on the bottom, I2 multiplied by Br2. And then we're going to get ready to fill these in with concentration values, reminding ourselves that the square brackets represent concentration. This one's nice and easy because I'm going to be taking these values and dividing it by 2. Okay, remember that concentration is equal to moles over volume, and moles for units is mol, and volume in this case is going to be liters. And that's what we want our units to be in for these questions. So 0.24 moles, well, that's going to be 0.12. This is going to be 0.25. I'm dividing all of these molar values by my volume in liters. And 0.4 is going to be 0.20. Okay, and these are all going to be moles. I'm just going to write on the first one. We're going to take these values, plug it into our equation. So 0.20 squared divided by 0.12 and 0.25. Again, these are going to be multiplied on the bottom, and I'm literally just plugging and playing into the equation we've already written. When you do this on a calculator, you're going to find that the numerator is 0.04 and the denominator is 0.03, which when you equate it out equals to be 1.33. And the only thing we need to do is think about the significant figures at this point. While this answer is acceptable, it's not 100% correct. If I look at my question, I can see that I have 2 significant figures in most of my units. And in this one over here, I also have 2. The 2 and the 0 are both significant for accuracy. So that means my answer can only have 2 significant figures. So the 1 and the 3. The 3 would round down. Okay, so we're going to truncate that and drop it, giving us a final answer of 1.3 for this question. Hopefully that worked out for you. If it didn't, please leave a question in the comments below or send me an email. Otherwise, we're going to move on to question 2. All right, starting question 2. Let's start by reading the question this time. It says, at 1400 Kelvin, an equilibrium mixture was found to contain 0.03 molar hydrogen. That's good. That's our units for this. We don't have to worry about converting this time. 0.046 molar, again good, sulfur in the form of S2, and 0.018 molar hydrogen sulfide. Great. Saves us some calculations. The question asks us to calculate the equilibrium constant Kc for this equilibrium given the following equation. Okay, so let's check. Is the equation balanced? H2S is in a reversible reaction with H2 plus S2. I can already see that the sulfurs are unbalanced. So let's put a 2 in front of H2S. That gives us 2 moles of sulfur, and over here we have 2 moles of sulfur. Then we have 4 moles of hydrogen, and I need to get 4 moles over here. I can do that really quick by just putting another 2 into the equation. Start by writing down the Kc expression. So Kc is going to equal the products. This time I have two products, so h2 square brackets raised to the power of 2 multiplied by s2 square brackets again, and we're going to divide that by h2s. Okay, so that's not bad. Nice and easy so far. Oh, and I almost forgot. There's a coefficient of 2 there, so we have to raise our denominator to the power of 2 as well. Next up, we do the calculations for this, or we plug and play our values. So this is going to be 0.013 raised to the power of 2 multiplied by 0.046. We're going to divide that by our hydrogen sulfide of 0.018, again raised to the power of 2. And when we do this on our calculators, I'm going to present the scientific notation here just for clarity. We get 7.77 times 10 to the minus 6. And our denominator is 3.24 times 10 to the minus 4. That's great. We do our final calculation, and I get an answer of 0.023, I believe 98. I'm trying to look back at my notes there. Again, we're going to look at the significant figures though. Okay, so we have two significant figures here, 2 here, and 2 here. So that means we have to truncate our number after this 3, and 9 is going to round up, giving us a final answer of 0.024. And if we want to present that in scientific notation, we would move our decimal over 2 spots. Okay, and this would become 2.4 times 10 to the negative 2. And that would be our final answer for this question. If you're just starting off with this content and you got an answer close to 0.02398, great. You're good. You're on the right track. If you want to push yourself, start looking at significant figures, and then once you get your significant figures down, start converting to scientific notation. This will help you out with future online courses if you ever have to put a value into a quiz or like a test online. So go ahead and pause the video here, double check your answer, and then we'll move on to question number 3. All right, assuming you've checked your answer, let's get started with question number 3. The reaction mixture below was examined in a 4-liter flask. Okay, that's important information to know, at 1700 Celsius. At equilibrium, there was 0.46 moles of CH4, 0.64 moles of C2H2, and 0.92 moles of H2. What is the value of Kc? So again, balance the equation. I can see off the bat already, carbon is off, so we'll put a 2. That gives us then 2 times 4 for 8 moles of hydrogen. There are already 2 moles here, so 8 subtract 2 is 6. And I have to think, what do I put here to get 6 moles? Well, 6 divided by 2 is 3. So there's a balanced equation. So we're good on that part. Then we start by writing down our Kc expression, which is going to be C2H2. Okay, remember products on the top. H2 to the power of 3. And then we're going to divide that by CH4, which is methane, and raise that to the power of 2. Not too bad. We fill in our values after we do our conversions. So reminder here, concentration is moles over volume. So I'm going to take these values of moles divided by my 4 liters, and I'm going to get a concentration value, which I'm going to plug into this question as we go. So the first one I got was 0.16, 0.23. Okay, so 2 values for the top. Raise the second one to a power of 3, and then divide it by 0.115 squared. Not bad. I do this on my calculator and I get an answer of 0.1472. So I've calculated the numerator and denominator. I've done the division. This is my final answer. If you're close to this, great. I would push yourself to use that scientific notation, which relies on significant figures. Again, 2 significant figures in this question. When you look at all the values, there's 2 significant digits. So we're going to truncate there right after the 4. The 7 is going to round up, which gives us a final answer of 0.15. And in scientific notation, that would be 1.5 times 10 to the minus 1. Again, if you got any of those 3 answers, great. You're on the right track. Hopefully this video is helpful, and thank you for watching.